Einstein's equation, Karl Schwarzschild, a famous German astronomer, discovered the formula that describes a black hole, but he did not understand the formula. He did not know it was predicting a black hole. But he discovered the formula that today we know describes a black hole that does not spin. In 1939, Einstein looked at the formula, he misunderstood it, and he disbelieved. He said basically black holes did not exist because he did not understand the mathematics. In 1939, Robert Oppenheimer at the University of California and the student Hartland Snyder, who had been a truck driver, he drove trucks for a living in Utah, they solved Einstein's equation to compute the implosion of a star to make a black hole. But they didn't really understand the mathematics that they had done. They partially understood it, but not at all well. It was not until the 1950s and 60s that these equations and the predictions were finally understood due to the work of a number of people, including my own mentor, John Wheeler. In 1965, Roy Kerr, a mathematical physicist from New Zealand, discovered the formula that describes a black hole that spins. And then in the 60s and 70s was what I like to call the golden age of black hole research, when Stephen Hawking and others really gave us the full description of what black holes are and how they behave. And in the 1970s, observational evidence for black holes began to come in. This is half a century that it took for physicists to understand the predictions of Einstein's equations and begin to test it observationally. It's a very long process, unfortunately, but we now have a very clear picture. As seen by somebody who lives in the bulk, who looks in on our universe from the bulk, this is the actual precise description of the warping of space and time near the black hole. Space becomes very strongly warped near the horizon of the surface of the black hole. The surface is a circle in this picture. It's actually a sphere, but you have to add one more dimension. Remember, I'm showing our universe with just a two-dimensional slice, segment of our universe. The color coding shows the slowing of time. The place where you go from green through yellow to red, time flows at about 10% of the rate that it does out at large distance. If the black hole spins fast, then this throat in the warped geometry becomes longer. And as the hole spins, it drags space into whirling motion like the air in a tornado. But it's space that's going around rather than air. And if you're very close to the horizon, you cannot avoid being carried by the whirling space around the black hole in the same way as a straw would be caught in the air in a whirling tornado. So these are the exact predictions of what would be seen by a bulk being looking in from the bulk, from the fifth dimension. Now, but what does a black hole look like to us? What would it look like if we were up close? For a non-spinning black hole, you can compute that by taking the warped space, depicted here again. You have a star at that location, you have a camera here. There are two light rays that can carry an image of the star to the camera. One goes around the black hole this direction, the other around the black hole that direction. And then there is a shadow where no light rays can come through from anywhere. And so the camera sees a black shadow, and it sees two images of the star. And if I place many stars here around the black hole, then you get this kind of an image. Here is the shadow of the black hole. There are the two images of this particular star. This is from a simulation, a calculation by Alain Riazuelo in Paris. For Interstellar, Christopher Nolan said to me, he said, "You help the team of Paul Franklin to compute this gravitational lensing for interstellar. And so I worked together with Paul. He introduced me to Oliver James and Eugenie von Tunzelmann in London. And we did a version of the same calculation as Maria Azuelo did, but for a fast-spinning black hole. And we invented and knew some new techniques for the calculation, because using the techniques everybody had previously used, when a star went across an IMAX screen, it would flicker, it would go bright, dark, and they were not able to solve that problem except by inventing a whole new way of doing the calculation, which I will not go into, but which we have published and is now being used both in Hollywood and by astrophysicists. Of course, Paul got the Academy Award for the visual effects in the movie, including as a major component to the kinds of things, of images of black holes and wormholes that I'm showing you. So here is a movie then of Gargantua, the fast-spinning black hole. It's a film clip. If it did not have a disk of hot gas around it. So if you look, you see amazing things as the camera is moving around the black hole.